Hi, this is continuation for power electronics lectures, and today we are going to continue looking at the buck converter. And in the previous video, we have seen how we derived the delta IL for the buck converter, which is the ripple of the inductor current here. And today we are going to continue to see the impact of changing the frequency, the inductance, duty cycle, and the output current on that ripple, because it's a very important parameter that we need to look at when we design a buck converter. So the starting will be with the frequency. So this is assumed frequency applied on the gate of this IGBT or this switch, and this will change the ripple here because that part is coming from the on time of that switch, and that part is coming from the off time here and on time of the diode. So the frequency in the equation tells us that if we increase the frequency, the ripple will decrease. And this is what we're going to see here, the ripple in decreasing in amplitude and also the frequency of the ripple, because the frequency of the ripple is the same as the frequency of your switching frequency. And the amplitude also decreased compared with the previous one, which is this one. Okay, so this is one type you need to consider in the design. If you want to decrease your ripple, you can increase your frequency. And this is an example of two buck converters, and one is supplied with 24 volt and running at 250 kilohertz, and the second is the same input voltage but at double of switching frequency here. The output is a 3.3 volt, and as we see here, both of them contains at least the same duty cycle. So here and there we have approximately the same duty cycle and the same output, so there is no difference. And I believe the same output current as well. We have here 1 ampere and 1 ampere. But what is the difference? The difference is the frequency. And as we see here, they looks identical. But if you look at the parameter here and parameter there, okay, so that tells us that each square here is 250 milliamp and each square here is 500 milliamp. That means we halved the ripple of the inductor current by increasing that frequency by double. And the second parameter we want to change is the inductance. As the equation tells us, the inductance decreases the ripple, and as we see here, we maintain the same frequency but we increase that inductance, and the difference will be shown here as reducing the amplitude of the ripple compared with the previous one, but the switching of that, or the frequency of that ripple, is the same as the switching frequency because it will not change. Okay, so this something that can be considered. But if you want to increase the inductance to decrease your ripple, sometimes you need to pay more cost because you are increasing the inductance by increasing the size, for example. But maybe you think about, okay, why I don't increase the frequency, because it's software matters. Okay, but the frequency increase sometimes it's limited by the speed of the high scientific frequency, or the speed of the switch, or the speed of all entire circuit, or other considerations. So now let's look at the duty cycle change. And when you look at that duty cycle, yes, this equation has two parameters here, which are the duty cycle, but they looks opposite to each other. Okay, so one increasing, one will decrease. Okay, so now the relation between the ripple current here and the duty cycle will be as this graph here. So the duty cycle, when it is 0.5 or 50%, the ripple will be at the highest or worst case scenario, and when you increase or decrease your duty cycle, your ripple will also decrease. Okay, so when you consider your worst case scenario, you should consider delta as 0.5, and that might be considered if I have different outputs here. So if I have here, for example, 100 volt input, and I want my output to be from 0 to 100, okay, so I don't have a specific output voltage, so I can really design my buck converter to that point, which is 0.5, okay, and that will be considered as a worst case scenario for delta I. If I increase or decreased the duty cycle during the operation of that buck converter, this will guarantee that the ripple will be less than the maximum that already designed for. Now let's look at the impact of the output current on the delta I, or the ripple of the inductor current here. And as we said before, the output current is assumed to be a constant value or without any ripple or ripple free, and all the ripple will be bypassed by the capacitor here. So if I increase the output current here, that means more current will be consumed from that node here, okay, or generated from that node to that direction. And does that increase or decrease the ripple? As the equation here tells us, there is no relation between the output current and the ripple. So if I increase the output current or decrease it, this will not affect the amplitude or the frequency of the ripple current here. But look at what's happening here. So if I have that ripple supporting that output current, which is high value here, so the output current is the average value here, okay, middle line between all that ripple waveform, and here the middle line, and here the middle line. So we are decreasing our output current. But what will happen now if I decrease it more and more and more? Now, if we are looking at what's happening here, the ripple current is always starting from a definite value, which is higher than 0, maybe 1 ampere here, goes to 3 ampere, reduced to 1 ampere, 3 ampere, and it's always positive, and it's always non-zero value, and it's always continuous. That's why if we have our buck converter has this inductor current waveform always has non-zero value, positive one, we call it, it's working under the operation of continuous conduction mode, or CCM. Now we can decrease the output current more and more, and that might happen because we don't have load, or the load is very small and doesn't consume lots of current. So what will happen? That current will be reduced also until the minimum value here reaches 0. Okay, so if we are now decreasing our load more and more, so the average value here tells us this is the output current. Okay, now if I made my output current very close to 0, that will reduce this waveform. So part of the waveform is this one, which is the on time, and this is the off time. Sometimes, yeah, I scale it because just to make it differentiated from the previous one. Okay, so this is the on time and this is the off time, but another part here appears, which is 0 ampere. Okay, so we have a duration for on time and duration for off time, and the duration for 0 or off diode and off switch as well. Okay, so 0 ampere here, again on, off, off, okay, or 0. So this one is called discontinuous conduction mode. Why discontinuous? Because the current going through my inductor is not always positive, and it's not always flowing through my inductor. That inductor tells me that it charges during that period, and this is charges during that period, and before the next charging instant comes, it turns to 0. Okay, so this is called discontinuous conduction mode, and it happens when my output current is very low. Okay, so now we have discontinuous conduction mode and continuous conduction mode. What about the blue waveform? The blue waveform is called the boundary conduction mode, which maintains the buck converter to still working in the continuous conduction mode, okay, but before going to the discontinuous conduction mode. So this is very important to know because they are very popular in DC to DC converters, and some designers, they try to avoid the discontinuous conduction mode, and some other designers for other topologies, they are purposely designed for buck converter to work just in the discontinuous conduction mode. So the benefits for that one and that one will be revealed later. But if we see some waveforms, and this is one of the waveforms here, okay, for the inductor current, I think we will agree that it's all above 0 and it's always continuous. So there is no 0 current passing through the inductor here. What about the voltage? So for this time here, the on time, the voltage is always positive and constant here. The off time, the voltage goes to the negative, Okay, so we have -3, for example, and positive and negative all the time. But what happens if we have discontinuous conduction mode? We have, yes, here charging or on time, we have here off time, but we have here the off period or zero period. Okay, so we call it here on, off, on for the switch and off for the diode, and here off for the switch and on for the diode, but here we have off diode and off switch. Okay, so we have this zero period here. So what will happen to the voltage during this period here, the on period? We have a positive slope for the current changing, that's why we have a positive voltage. Negative slope, negative voltage, but we have here zero value for the current, that means zero value for the voltage. So that's why we have 3 levels here, not 2 levels like this. So what are the reasons for discontinuous conduction mode? Low output current when we supply light loads, or small inductor value. The inductor is so small that doesn't maintain the continuous conduction mode during the charging and discharging. So it charges very fastly and discharge very fastly. And this will make the current disappear before the second or next instant of charging. Okay, and sometimes if you have very long switching period, so it will discharge before the next charging instant will come to charge it again. Okay, so these are some other examples, and maybe we have mentioned before that this is the on time, okay, where we charge the inductor, and this is the off time, and this is the off or zero state, and this is what we are expecting from the voltage across the inductor. But actually we don't have this period here as steady period or constant period. We have practically this phenomena here. What will happen? The on state, yes, we got positive voltage across the inductor. The off state, we have negative voltage across the inductor. But when we have the zero state, there is some oscillation will appear, and that oscillation is determined by the resonant loop formed by the inductor and the parasitic capacitors of the Mosfet and of the diode. So we have here some capacitance in the circuit, maybe that capacitance, and this there is some capacitance here, parasitic capacitance, and also that diode still have some parasitic capacitance beside the parasitic capacitance of the board itself and the PCB itself. So all that together will produce some inductance in series or in parallel with some capacitance, and this will produce resonant like this. So we don't have a steady zero voltage here, but we have some resonating voltage here, and this appears always in our circuit. So if you found your circuit has this current, okay, oscillating current around zero here, or oscillating voltage around zero here, that means you are running now in discontinuous conduction mode. And this is just another example. Also we have the on time and off time, so our inductor has it discharged the current very quickly, and now turns to the zero but oscillating current here. We have 3.3 voltage output, the input was 6 volt, and the output current 0.1 ampere. That's why we run into the discontinuous mode, because the load is consuming very minimum current here. So this period here, it's supplied by the transistor, and that period is supplied by the diode, but this period is not supplied by anywhere. The diode and the switch are off. So now let's look at different aspect, which is the minimum value of inductance needed to make us still working in the continuous conduction mode. So as a designer, you should know what is the value of inductance. You can change the frequency, you can change the duty cycle, yes, but sometimes you are limited, and you want from the beginning to determine that you want frequency of 10 kHz or 20 kHz, and you want to stick with that, but you want to design your buck converter to work always in the continuous conduction mode and never goes to the discontinuous conduction mode. So what is the minimum value of the inductance that makes the buck converter always works in the conduction mode? So if we now assume the boundary condition, we have this rebel here, and that rebel, the minimum value, we can consider it as 0. Okay, so the rebel, when we have the boundary condition, the rebel will go to the very big or very maximum value and goes to 0. maximum value goes to 0, okay? And the average voltage supplied to the output load, it will be the average value here, okay? So what is the relation between the average value and the amplitude of the or peak to peak of that ripple? I think you will agree with me that the ripple from maximum to minimum will equal 2 times of the output current, the average value here, okay? And that's appearing from that graph, because the distance from that middle to the minimum equals the distance from that middle to the maximum. So that means delta I equals 2 I output. From there, we can really replace that one as 2 I output here, okay? And from that equation, we can derive that the minimum L, okay, required to maintain our buck converter into continuous conduction mode should be this equation here, which is delta 1 minus delta V input, which is this part, divided by 2 Fi output average. So if I want to make my buck converter continuous conduction mode in minimum load current, so I should put my minimum load current here, and then I really design my inductance here. And this is the minimum inductance to keep the converter in conduction continuous mode. And if you reduce it, you will probably go to the discontinuous conduction mode. So what is the disadvantage of continuous conduction mode? It seems that we should always consume current. It doesn't work in continuous conduction mode if we have no load, because this will be 0, and that means we can't actually maintain that equation. And this is one thing that you should, as a designer, look at. If you are looking at continuous conduction mode, you should remember that you should always consume current from that buck converter. And if you stop for any reason to consume that current, your buck converter will go to discontinuous conduction mode. And if you know the resistance of your load, always you want to design it for some resistance, you can just, because we know that delta Vn is V out and this is I out, we can replace it with our load, okay? So this is the resistance of the load if we are designing our buck converter for a specific resistance load. So this is the way of choosing our inductance. And now there is very important question. We know that in continuous conduction mode, we derived the equation for the output current, which is V out equals delta Vn. Now, does that still working for the discontinuous conduction mode? The answer is no, because all the derivation now is different, and the on time and off time, the two modes that we considered in deriving this equation, is now different. And the new equation for the V output for the discontinuous conduction mode is this complicated relation here, okay? As we see here, we have V input squared divided by 2 LFI output. So our output voltage now has a relation with the output current or the load. And this is one of the disadvantages of discontinuous conduction mode. Your output voltage will change with the output current or output resistance. And if you want to maintain the same output all the time, you have to get feedback, and you should design a controller for that and reduce or increase the duty cycle. So you see that now it's very impossible to have a very linear relation between V output and V input. We have square here and we have square there, okay? So it's the relation between the input and output is non-linear, and always it's load dependent. So now let's consider an example for continuous conduction mode, where we have the V output equals delta V input. We have this delta I, we have this variation of the output voltage, and we have this circuit, and we have the step down. This DC converter has an input voltage of 15, so V input will be 15. The required DC output voltage is 5, so 15 here and 5 there. From 15 here and 5 there, I think we can calculate the duty cycle. This is one thing that we want to remember. And the peak-to-peak output ripple current is limited to 0.5 ampere, which is you as a designer should choose it, okay? So this one is maintained to 0.5, and we can really choose now the inductance if we have the frequency. And the peak-to-peak output voltage is 10 millivolts. So if it's 5 volt, we want just 5 volt to just play or just a change within 10 millivolt. Okay, the switching frequency is chosen to be 10 kilohertz. So we want to know what is the given V input 15, V output 5, the delta I 0.5 and delta V 10 millivolt. What is the first requirement is calculate the duty cycle, and I think it's very easy because we have this relation. We can use it to just substitute the V input and V output, and it will be 5 divided by 15, and this will give us 33.3% or 0.333. Now, what's the second requirement is the inductance. I think we are looking to the available equations, and we see the inductance can be calculated by this equation if we know delta I, if we know the frequency, if we know Vn, and if we know delta, and all are known. So we can use this and just substitute the all the values in the inductance equation, and we can get it as 0.66 millihenry or 660 microhenry. Okay, so this doesn't actually tell us if it will work in discontinuous conduction mode, but we assume that it's continuous conduction mode. If you want to test if this will, if it's the minimum or more than the minimum for continuous conduction mode, we have to recall the equation for the minimum continuous conduction mode inductance. So now the third one is the output capacitance, and I think the output capacitance is this equation. We know all the other parameters, and we can just really substitute all these values in our equation, and the final value will be 628 microfarad. So this is what we call a design, but you have to know some parameters before that just to make your design successful and realizable. So in the coming video, we are going to consider talking about some considerations for the design of the buck converter, maybe the parasitic parameters or thermal consideration or other things. So see you next video. Thank you.